All right, so we have two ways that we are mentioning to evaluate this function. We can use direct substitution. Direct substitution would be replacing every single x that you see there with a parentheses and a -1 inside there, which might not be too bad. -1 is a pretty reasonable number. But we learned yesterday that there's also a synthetic way to do it, right? Phones away, right? A synthetic way. Here's how we'll do it. We'll practice the other way some other time. Direct sub. Today we're practicing synthetic sub. So we write the coefficients in descending order, and remember we need a placeholder if there's anything missing. So 2x to the fifth, -3x to the fourth, 2x cubed, -1x squared, and 2. There were no missing powers of x, were they? So we had a placeholder for everything. And then we draw the line, and we put the box here, and we put the box here. What number goes in the front if we want to evaluate it at -1? -1. Oh yeah, just x. I'm sorry. I created this problem to have a missing one, and I tricked myself. There is no x there. Good eye, Arlie. There's no x. So what do we have to have as a placeholder there? A 0. Yeah. Okay. I tricked myself. I'm just going to blame that on the brain damage. How about that? All right, so once I have all the coefficients with my placeholder, I put the -1 out front because I'm synthetically substituting a -1. And then I do the process, which remember, bring down the 2, multiply on the bottom, and then add columns. So we get a -2, we add, we get -5, we multiply, we get 5. 5 plus 2 is 7. Multiply by -1, we get -7. Add, we get -8. Multiply, you get 8. 8 plus 0 is 8. Multiply, you get -8. -8 plus 2 is -6. And there's your answer. There's your answer. So f of -1 equals -6. And there is an ordered pair on that graph called -1, -6. There's a point on that graph of that fifth degree polynomial called -1, -6. Now remember, if we think about it in terms of synthetic division, which is just a slightly different way to look at it, here's what the synthetic division would look like. Okay, this is substitution. And then here's the division. The division would say that 2x to the fifth minus 3x to the fourth plus 2x cubed minus x squared plus 2, all divided by what? If I synthetically substitute -1, what is the factor that's the divisor? Is it x -1 or x plus 1? Plus 1. It's the opposite, right? The factor is the opposite, because -1 is the root of x plus 1. So if I divide by x plus 1, then I get the quotient. What would the quotient be? We actually, like when we do synthetic substitution, we're really milking this entire process for all it's worth. Those numbers that I just highlighted right there, remember what those are? Those are your coefficients of your fourth degree polynomial. So that's going to be 2x to the fourth minus 5x cubed plus 7x squared minus 8x plus 8. Those are the coefficients of your quotient that's 1 degree smaller. And then the remainder is going to be plus -6 over the divisor x plus 1. Or you could just say -6 over x plus 1. So the process itself is identical, whether we're calling it synthetic substitution or synthetic division. The only difference is, what are we after? Okay, are we after the function value, in which case we don't have to do all that extra writing? Or do we really want to write the division process as a quotient plus the remainder over the divisor? Everyone good? Everyone got it? Okay, great, super. Let's look at the remainder theorem. I've studied the remainder theorem for years and years and years, and this is the most poorly worded remainder theorem I've ever seen. Okay? I don't like the way this remainder theorem is worded. So here's what I'm going to recommend we do. I'm going to recommend that we box all that and then draw a line through it. Boo, boo. Okay? I'm going to give you a different, more concise definition. Here's what it says. If P of x is divided by x minus a, comma, the remainder is P of A. That's it. And we already know this. This is just a summary of what we've just done. When you divide by x minus A, the remainder is nothing more than the function value at A, just like we did in the warm-up, okay? When you divide by x minus A, the remainder is nothing more than the function value at A. It's the last little box there in the synthetic division process. Let's see how we can use the remainder theorem to answer a question like this. If P of x is 2x cubed plus x squared minus hx, what is h? Ooh, we don't know. If that has a remainder of 1 when it's divided by x plus 3, what's the value of h? Oh, okay, we're trying to find h. So here's what we're going to do. We're going to do the same process that we've been doing. This is our dividend right here. This is our dividend. And the divisor is x plus 3. But now they're giving us the remainder. So we know the remainder is 1. So let's go ahead and set out our coefficients in descending order of degree. And I'll try to be a little bit more mindful if I'm missing something here. So I got a 2x cubed. I got a 1x squared. I got a negative h as my coefficient of x. I'm just going to leave it as negative h. And then I got a constant of 7. I don't know what h is, so I'll just put negative h. All right. I am going to draw my line, and I'm going to create my two little boxes, the one in front and the one at the end. Now, let's fill in what we know. When we're dividing by x plus 3, if that's the factor, what goes in the front box? 3 or negative 3? Negative 3. The opposite of what the factor is, right? If x plus 3 is the divisor, we always synthetically substitute or divide with a negative 3. And now we know what the remainder is, right? The remainder has to equal 1. The remainder has to equal 1. Well, let's go ahead and do the synthetic process. Bring down the 2, multiply, you get negative 6. Add, you get negative 5. Multiply, and you get 15. Whoa. Now, what do we do here? What's 15 minus h? No, that would be 15h minus 1h. Are those like terms? No, they're not. So I just put 15 minus h. That's all I put. I put 15 minus h. Yeah, now times negative 3, since it's two terms, I have to distribute, don't I? I have to distribute. What's negative 3 times 15? Negative 45. And what's negative 3 times negative h? Positive 3h, right? Positive 3h. No big deal. I can have polynomials in here. And now I add vertically. When you add vertically, remember, you only add like terms. So I add those constants together. What's 7 minus 45? Minus 38. And then the plus 3h just comes straight down. There's no like term to combine it with. That's my remainder in terms of h, isn't it? But guess what it has to equal? It has to equal 1. Okay, so I know that 3h minus 38 has to equal 1. Can we solve that for h? Absolutely, we could solve it for h. This is Algebra 1 stuff. We'll add 38 to both sides, then we get 39. And then I divide through by 3. And what's 39 divided by 3? 13. So h is 13. But easy, right? It's the same process. It just sets up as an Algebra 1 equation on the back end of it when you set the remainder equal to what's given. All right? So anyway, that's how you work problems like that. All right, the factor theorem. I've studied the factor theorem for years and years and years. And this is the most poorly worded factor theorem that I've ever come across. Okay? So let's do this. Let's put this in a box. We'll draw a line through it. Okay? And we'll write our own factor theorem. Here it is. X minus A is a factor of P of X if X, or I'm sorry, not if. It's an if and only if. So X is a factor of P of X if and only if. So we'll use a double-headed arrow. X equals A is a root of P of X, which means that P of A equals 0. Okay? If and only if means it works both ways. So if you know a root, you know a factor, and if you know a factor, you know a root. If you know a root, you know a factor, and if you know a factor, you know a root. We've been using this quite a bit. Here are some examples of the factor theorem. If x plus 3 is a factor, then what's the corresponding root? Negative 3 is a root, or 0. Okay? Here's another example. If x minus 5 is a factor, or we could do it in reverse. Let's do it this way. If x equals 5 is a root, then what's the corresponding factor? X minus 5, I'll put in parentheses, is a factor. You just take the opposite, right? If you know one, you know the other. That's what the factor theorem tells us. If you know a root, you know a factor, and if you know a factor, you know a root. Now, what does it mean for something to be a root? It means that the function value there is 0. Okay, it lands on the x-axis. Okay, so let's try this out. Use the remainder in the factor theorems. That sounds like that's quite a big charge, right? Like, ooh, I got to use the theorems, right? To determine whether the binomial x plus 1 is a factor of P of x, which is an x cubed. Well, we've already talked about this yesterday. If a divisor happens to be also a factor, what should the remainder be? 0. Okay, that's what this says. The function value there should be 0. So let's just check. Let's just check and see. So I'll write out my coefficients of my dividend. X plus 1 is your divisor, for sure. But is it also a factor? Question mark. I don't know. Let's see. So I write out the coefficients. 1x cubed, 3x squared, negative 6x, and negative 8. There's nothing missing. What value do I synthetically divide or substitute with? Negative 1. That's the factor theorem. If x plus 1 is the factor, negative 1 is the root. And let's just see if I get a remainder of 0. Bring down the 1, you multiply, you get negative 1. 3 minus 1 is 2. 2 times negative 1 is negative 2. That gives us negative 8. Negative 8 times negative 1 is 8. 8 minus 8 is what? 0. I got a remainder of 0. So is it in fact a factor? Yep. So here's what this means. That means that x cubed plus 3x squared minus 6x minus 8 happens to equal x plus 1 times some other function f of x, which will be a quadratic. So sometimes, if you don't know how to factor by grouping or by factoring by any other method, you can almost do like a guess and check. You could say, is x plus 1 a factor? Well, let me try negative 1. If it is, I got one of the factors. Okay? Now, do we know what f of x is? Is there a way to figure out what that other factor, f of x, is? The answer is absolutely. Because what do those numbers right there represent that I highlight? Those are the coefficients of your quotient. So it should be 1x squared plus 2x minus 8. So we have a partial factorization of the cubic polynomial. It's x plus 1 times x squared plus 2x minus 8. Does x squared plus 2x minus 8 factor any further? Can we double bubble that? An x and an x, a 4 and a 2, a positive and a negative? Yes, yes? Oh my gosh. So I can't factor P of x by grouping. If you tried factoring it by grouping, it wouldn't work out. You wouldn't end up with the same thing. So we actually don't need to factor by grouping because they gave us a little clue as to one of the factors. So here's what we know. We know that x cubed plus 3x squared minus 6x minus 8 is actually equal to x plus 1 times x plus 4 times x minus 2. Synthetic division is a tremendous aid to factoring when you know one of the factors already. Okay? You can get the quotient by just looking at the coefficients. So, we already answered the second part. If x plus 1 is a factor, factor p of x completely. We just did that right there. Fantastic.
So that's the final answer?
That's your final answer right there. There's two answers here. To answer the question, is x plus 1 a factor of p of x? Yes. There's the first answer. Yes, it is a factor. Therefore, we can factor that as x plus 1 times the quotient, which is the coefficients there, 1x squared plus 2x minus 8. And once we get to that quadratic trinomial, that's the quotient, we can factor that by just double bubbling it. Okay, and we take that with the other factor of x plus 1 to get all three of your linear factors. All right, check for understanding. Let's just go through these and see if you agree with the answers. How can you tell if you are finished solving a polynomial division problem? In other words, how do we know that the process ends? When the remainder has a degree, remember, that's less than the degree of the divisor. Or you get down to a constant. Okay? X squared can go into x squared, but x squared can't go into x to the first. That was the first problem that we worked at. What do you write as the final answer for a polynomial division problem? Your answer should be written as your quotient plus your remainder over your divisor. In fact, I would like for you to write the whole thing out like we did in the warm-up right here. The whole thing, which would be the quotient on the left equals this plus the remainder over the divisor. Or, I'm sorry, the original problem, I called it the quotient. The quotient is 4x squared minus 5x plus 12. That's how you write your answer. Okay? Compare long division and synthetic division. The numbers generated by synthetic division are equal to the coefficient of the terms of the polynomial quotient, including the remainder. They are essentially the same process. They are, but the synthetic division process doesn't involve the x's, right? And it's a lot more streamlined. It's just multiply and add, multiply and add, multiply and add. What conditions must be met in order for to use synthetic division? Super important. It must be what? Linear, and the coefficient of everything that you're going to see has to be a 1. You can actually do synthetic division when the coefficient isn't 1, but you have to synthetically divide with the root of the polynomial. Okay? We're not going to get into that in this class. We'll do that in pre-cal next year. Right? So yours are always going to be not of the form mx plus b, but they'll just be of the form, they'll just be of the form x plus b. Okay? 1x plus b. What operation are you doing, and what are you finding when you use synthetic substitution? Well, we already said that. You're dividing p of x by x minus a, but you're also finding the value of p of a. They mean the same thing, right? You're finding the result when you do p of x divided by x minus a, and the result is written in this format. But you're also finding p of a. When do you use synthetic division, and when do you use synthetic substitution? That's a pretty good question. It all depends what the question is asking you. Use synthetic substitution when you want to find a function value, a specific value like in the warm-up. What is the function value at -1? That ends up being the remainder of the division process. And then you use the synthetic division when you want to find the actual quotient. Okay? The actual quotient. How does knowing one linear factor of a polynomial help you find the other factors? Well, if one linear factor is known, you can use synthetic division to find the other factors, which might be easily factored. Case in point, example what? Example 5. That's what we just did. Example 5. How do you know when the divisor is a factor? When is the divisor a factor? When the remainder is what? 0. Yeah. How are the remainder theorem and the factor theorem related? Well, the remainder theorem just says that the remainder is the function value evaluated at a. The factor theorem goes on to say when that value is 0, then it's also going to be a root of the polynomial. Okay, so they're kind of related. The remainder theorem just is the general thing that says f of a is the remainder, and if that remainder is 0, it's a factor. Okay, and that's it. So we got through the whole process. Most of it was yesterday. Today was just kind of reinforcement and cleaning up a little bit. And that's all I have. Y'all have any questions? There's an assignment waiting for you in Canvas called 8.4 HWQ. And it's all yours. It's all yours to do. We will make the homework due on Friday at 9 a.m. So you have the rest of the class period to finish working on it, okay? All right.